Sorry. I made an introduction. It was beautiful, but basically for the people online, we'd like some critical feedback at the end because we've gotten comments from reviewers that they don't believe us. So it would be good to have you say how we can make this more believable. So with that, Caleb, go ahead.
Yep. So hi, everybody. My name is Caleb Manicke. This is a project that I've been working on for, I think, the past year and a half on voting security. It combines a lot of topics from machine learning to adversarial, to adversarial text and its applications in voting security. So again, a lot of feedback is appreciated. Please make any comments you'd like. Let's just get into it. Do I have to press this? Okay, so here's the very brief rundown of everything. Is in bubbled ballot data sets. Everybody has to put down a mark in order to vote for, Mickey Mouse, Donald Duck, right?
Khalid, we can't see anything.
Did I not share?
No.
Better to see now?
Yeah.
Thank you, Amir.
I'm going to increase the volume on this end. So can you guys hear me now?
Yes.
All right, let's redo that. Hi, everybody. My name is Caleb Manicke. I'll be presenting a project that I've been working on for the past year and a half. This combines a lot from deep learning, adversarial machine learning, and voting security. So it's a very, very interdisciplinary project. Please feel free to ask any questions in the middle of the presentation, and I'll try to get back to you with the best answer I can. But this work has been in review for a long while, so comments and feedback are much appreciated. So let's look at the overview. Everybody has to vote, or at least you should in a democracy, right? But not all marks are created equal. So if you want to vote for, say, Mickey Mouse or Donald Duck, maybe a lot of people, they opt to put in an X, or maybe the way that they shade in their bubble isn't as dark as it should be. And these may not be picked up by the traditional light sensors that they traditionally use to classify marks. So in this sense, deep learning classifiers are kind of seen as a method to pick up on these non-traditional marks. But whenever deep learning classifiers are introduced, there's always security concerns that come with these. Specifically, there's an entire field that is dedicated to creating imperceptibly perturbed, quote unquote, adversarial examples that, they look like a dog to you and I, but to a classifier, that's a cat, right? And we've been able to create this heuristic that allows adversarial attacks to generate, these examples that will then go on to be misclassified by any machine learning classifiers that we train in our voting data set. So the goal of today's presentation is to really explore this vulnerability, both on, virtually processed ballots, as well as ballots that will print and scan and register and feed through our classifiers. But before we gain any ground, we have to start from the very beginning, how machine learning classifier training works. Machine learning, it's a huge field, especially with the advent of deep learning. Everything has really popped off, but in hindsight, all machine learning models kind of do the same thing. They do something called feature extraction. And what that means is, given any data point, they're going to learn to represent this data point in something called a feature space, which we can kind of think of as like an arbitrary subset of the real space. And from this feature space, it's going to learn how to draw a line, our decision boundary. And our decision boundary is what separates our classification domains. So in this picture over here, right, we'll see that this line is dividing between what feature vectors count as a dog, what counts as a cat, right? But when we're just initializing a model, we're not really expecting our decision boundary to be right, right? There's going to be, right, and you'll see in this example here, Mr. Whiskers, he's being classified as a dog. That's not right. We want him to be a cat. So what are we going to do? Well, from this decision boundary, using our current model weights, we can compute something that's called a loss function, which will give us the distance between an image and its decision boundary. And from here, we're going to take the gradient of this loss. This is going to be the direction from our data point to our decision boundary. But we're not really going to try to move the image towards the decision boundary. We want to move the decision boundary to fit towards our data point. In this case, we kind of want it to fit over Mr. Whiskers, right? So we're going to multiply this by some learning rate term. Here we denote it as alpha. And we're going to subtract alpha times we're going to subtract our current decision boundary by moving it in the direction towards the example that we want to train on, multiplied by our learning rate. And that kind of regulates how much we want our decision boundary to fit to this example. So very formally, this is known as gradient descent, right? Our current weights subtracted by themselves times some alpha term with the gradient of our loss. And with a larger loss comes a more drastic fitting towards our training image. So something really interesting comes over here, right? In the sense that gradient of our loss is calculated with respect to our decision boundary and our image. And in the training context, we're trying to move our decision boundary. But if you're cheeky, you might think about, what if we're trying to move our image? And this is how we get into the field of adversarial machine learning, right? So imagine, per se, that we get the gradient of our data point with respect to our decision boundary. So this is the direction in which we have to move our image to get to our decision boundary. Or in the case of training, this is the negative of how we have to move our decision boundary to fit towards our image, right? So imagine we're going to add, instead of an update term to our decision boundary, an update term to our image, right? And we're going to do this by essentially adding some noise. We're going to interpret the gradient as the direction to our decision boundary. We're going to take the sign of this. So anything that's negative is just going to be a -1, and the 1 is anything that's positive is just going to be a 1. And we're going to multiply all of this by our epsilon term, which in adversarial attack literature is known as the perturbation factor. But very informally, this is kind of the magnitude in which we're going to move our image towards the decision boundary. And if our perturbation factor is large enough, it should cross over our decision boundary and be misclassified, right? This is very powerful, and it's very concerning. What we just showed here is the most basic adversarial attack, known as the fast gradient sign method. And you can imagine the literature gets a lot deeper. So let's get into that. What are the types of adversarial attacks that we could think about? So we just showed what the fast gradient sign method is. We're just adding one update term, right? We're just going to take the gradient loss with respect to one image, preferably a correctly classified image, because we want it to be misclassified. And we're going to move it all the way hopefully towards our decision boundary, so it'll overstep that and become misclassified. It'll enter from one classification domain into the next. And from here, you can imagine, okay, well, if we're just, updating some data point, then what's stopping us from just taking an iterative approach? And that's exactly where the literature moved towards. Specifically, we have the PGD attack, known as the projected gradient descent attack. And all we're doing here is just adding an index, right? And instead of an epsilon, we're adding an epsilon step term. And you can imagine that for how many n iterations that we want to add adversarial signal to our example, that epsilon step is usually going to be, say, our epsilon max over, the number of iterations that we're giving our attack. This proved to be more effective.
What's wrong with FGSM?
What's wrong with FGSM? There's nothing wrong with FGSM, but PGD is more sophisticated. Specifically over here, you can see that once we already crossed the decision boundary, now the direction in which our adversarial example, our example is going to be pointing towards the decision boundary. It's going to be in the opposite direction. So now we can focus on minimizing the amount of adversarial noise.
Can you tell us a little bit how epsilon, the collection of epsilons that relate to one another? What are the requirements in epsilon, if any?
Absolutely. So
that we can start to see.
absolutely. So epsilon step, usually it's the maximum so okay, informally, epsilon is the maximum amount of perturbation that you can add to an image. And usually we want to keep this as low as possible so that any adversarial noise that we add to our image is going to be imperceptible.
Let's make it clear. X here is an image, right?
Yes.
So this is a 2D object where every pixel is a triplet, RGB.
Yes.
So what is epsilon? It's a matrix of the same thing.
Oh, it's just a constant. It's just a scalar
That we have to what?
that we add to, yes. It's a scalar that we multiply by,
Because an orange is
no. Our
just a set.
our sign gradient loss is going to be the dimension of the image. So we're multiplying this by our scalar term. So we can control the magnitude at which we're descending past the decision boundary.
So sine delta L is a 2D matrix of triplets.
Yes. Yes.
That are all plus or minus 1
Yes.
in the triplets.
Yep.
Then
And-
you scaling that pointwise by a constant epsilon.
Yes.
You end up having 0.001.
Yep.
0.001 minus 0.001. And that's a big matrix like that. And that's what you have to do.
Exactly. Yep.
So let me ask my question again.
Yep.
Why we don't improve on things that aren't broken?
Yep.
So why do you need to improve on GSM?
Because we want to keep the total allowed amount, the amount of total perturbation that we're adding to our image as small as possible. When we're just doing a singular update term, we're just adding the maximum amount of perturbation allowed. Right? Whereas with PGD, once we already cross over the decision boundary, we can start optimizing how much perturbation is going to be with respect to the original image. So the total amount of perturbation added to, in our adversarial example, when we compare this to our original image, is going to be smaller while still being misclassified.
All right, so now connect this back to gradients. So what's going on with gradients that FGSM wouldn't be the right thing to do?
Because since FGSM is only a one-step attack, only thing it's focused on is just stepping over the decision boundary. But imagine if epsilon was large enough, instead of being close to the decision boundary, maybe it'll be way over here, right? Whereas if you have enough steps with PGD, once you get it, you will never really get way over here. You'll take steps and then you'll try to get close to the decision boundary while still remaining in this area. Because now our gradient loss term, right, once you're over here, it's going to be pointing over here, so we're going to move in this direction.
So stay on the computer. Use your mouse and cursor.
Oh. Okay.
And I'm here as a question.
Yes.
I'm sorry for a question which is a bit kind of outside this, which is I try to understand the reality of this attack model. If I understand correctly, you assume here that the attacker is able to provide you with these modified pictures, and
Yep.
also that the attacker knows exactly your current parameters. Is this correct?
Yep.
And how realistic is this? I mean, I know you're now talking about dogs and cats, and maybe it's an image processing system in a phone, so that's available to the attacker. But I know that your goal in your talk is to talk about voting, and I'm trying to understand what is the scenarios that we are talking about. How would the attacker have all of this, both the ability to provide these bad examples, as well as the ability to know exactly the parameters? And also in the voting example, at least I would really have assumed that you would not have like a black and white dogs and cats, but also you will have, the area where the system tells, I'm not sure, and right, and then you have a manual verification. No, maybe I would assume
That's an excellent question. That's exactly what we're going to get to in the next couple of slides, is with voting as well, right? There are multiple scenarios in which you can try to, say, compromise a voting system that will then add this adversarial signal, which will fool a machine learning classifier, right? And what we talk about later on is the process of voting itself. The process of printing and scanning ballots itself may actually dim our adversarial signal, right?
So you're going to explain how the adversary is able to get all of these. So to get, for example, to do this permutation at the learning process and to know the parameters, you're going to talk about that? You're going to explain that this is a realistic attack?
Yeah, so we're working under the threat model that we're working under now is that there is a printer or a ballot marking device that has been compromised.
He asked you about knowing the weights.
About knowing the weights. Yes, that's
It's public and what's secret.
But he's asking.
So
he's
I mean,
asking,
if the printer is compromised, why couldn't it just print whatever ballots it wants? Well, it wouldn't be, right? I mean, that's not in the learning process, is it?
because
I'm going to step in for a second. So Caleb's going to talk about two different attacks, but if I'm a printer, I want to print ballots that look empty because people are going to look at them before adding marks.
Okay, you're okay. I got it. You're printing the ballots empty, and then people are going to add this pencil using a pencil or a pen or whatever. Okay, and you want that after the scanning, they will have whatever your preference is.
Some of those marks that looked empty were actually classified as full.
So you're completely.
Wait, I haven't answered his question. So the other part of your question about knowing parameters is the current voting system guidelines that were published in fall of 2022 say you are supposed to publish how your classifiers work.
How classifier works means you're supposed to publish your parameters?
So nobody has actually been certified under this process, but they say you are supposed to provide a detailed explanation of how your mark interpretation classification works.
Sure, but that's very different from providing you parameters.
I agree. Agreed. So Caleb will talk a little bit about black box models too.
Okay.
But like this is, and there are open source voting system vendors that publish everything.
Okay. Okay. So one could say that at least what you're doing is at least evaluating the importance of not publishing, or is it important not to publish?
Right.
Or is it
And
fine to publish? So,
this is a tricky thing because voting system vendors notoriously hate to share things. And I don't want to give them more reason to not share information. But yeah.
yes, but maybe of course that's there is a good reason not to share, right? Yeah. Okay. Yeah. Interesting. Okay. Continue. Thank you.
Yep. So you're completely right, Professor Hertzberg, is that if, say, a printer or a ballot marking device is compromised, then there's no stopping an adversary from adding as much noise or printing out whatever they want. But a successful adversary will limit the amount of noise that they print so that whatever signal ends up on the ballot is going to be imperceptible to the people who are going to be registering these ballots afterwards. Sorry?
Yeah, I just want to comment that if I were to design a voting system, I would assume that the paper used, for marking is independent of the choice of the entire of the candidates. Like, I mean, this should be, and I think actually that's what happens in practice, right? The printing of this is not related to a particular vote, so you shouldn't know even which candidate is which result. But so to me, that actually seems to be quite a big problem for these attacks in reality. But I don't know, maybe I'm wrong.
We'll explore that later on.
Oh, great. Thank you.
Yep. So immediately getting into it is we're going to switch out the cats and dogs for votes and non-votes, right? Immediately, this seems like a very easy problem, right? And we already have hardware light sensors and tabulators to detect. Is there a darkening in this bubble or is there not? So why would you want to use deep learning in this scenario? Well, not all bubbles are filled in equally. There are people who maybe put a little scribble at the end of their mark when they really should be filling out a bubble. Sometimes there are things called pen rests, where somebody will just rest their pen on a bubble, and that may get misclassified as a vote. Maybe it is a vote. And there are people who will maybe cross out a bubble, right? We've all probably seen examples like these. So this is your incentive, is that a deep learning model should very, 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 very easily be able to classify what a filled-in vote, as well as a filled-in non-vote is, as well as any examples in between. But this means that whatever decision boundary our model is going to learn, it's not going to be as cut and dry as, yes, there's a dark spot. No, there's not a dark spot. This distorts our decision boundary. This can distort a decision boundary. We can't necessarily claim overfitting them, right? So what we want to know is if we train on these marginal marks, will it somehow compromise our model susceptibility? Will it be easier to run these adversarial attacks and create more imperceptible adversarial tools? Okay, so let's get into our experimental setup. Let's consider all of our models. The most simple model that we're going to be using, it's support vector machine with a linear kernel. We're not really expecting this to generalize to marginal marks. This is the simplest thing we're using. It's just going to say, just a dark spot. No, there's not really a dark spot. And it's going to maximize that class-wide distance. That's what a support vector does. We've created our own convolution-based network, which we call the simple CNN, because it is that simple. It's just 3 convolutional blocks for a total of 30,000 trainable parameters. And then we get into the very classic residual network. Specifically, we're using the ResNet with 50 layers. This has 100 1,000 parameters, uses residual connections to connect ResNet blocks, so to prevent the vanishing gradient problem. And the most advanced architecture that we're going to be using is the twins model. So in natural language processing, probably the most popular architecture as of now is the transformer, which is used to, say, take a sentence and map something called an attention matrix onto that sentence. So, and that attention matrix is going to learn how much each letter or word is correlated to the next. And what people found is we can apply the same thing to vision models in machine learning by interpreting patches of images, turning those into feature vectors and then taking attention matrix on that. So there is at the local level, we're interpreting these patches, and at the global level, we're learning how these patches in our images are related to one another. But the overall thing that you need to know here is that not only is our architecture getting more complex, but the number of training parameters that we have to consider is also increasing almost tenfold with each example. So let's consider our data set. We have around 35,000 non-marks and 7,000 marks in our complete data set, but we're mainly concerned about these marginal marks, right? So what we do in this scenario is we create these synthetic swatch examples, right? Which you'll see on the right to this image by using the linear kernel of an optical scanner. So these are the synthetic examples that kind of are just on that board, right? And we're providing this as more training examples for our classifiers. So we're going to consider two scenarios here. Our bubble data set, which is only going to consist of nicely filled in marked bubbles and bubbles that weren't filled in, as well as our combined, where we're going to add these swatches as well. Oh, good. So in the example here, we're also varying if we're going to be training on colored examples. So all of the ballots that we used, they come in multicolored backgrounds. So they're going to be pink or light blue or purple. But the most realistic setting is to train on grayscale, right? Most of our ballots are going to be black or white. Almost all of our marks are going to be some shade of gray. So we considered so for the purpose of this presentation, we apply a manual grayscale conversion to our ballot data set, but we do also consider the color data set. But for the purposes of this presentation, we're mainly considering, our grayscale models and a manual grayscale conversion on everything. Does that answer your question? Okay. All right. How do we train our classifiers? So we're just going for each model that we consider. We're going to be training them on the combined and our bubble data set. So just something very quick that we had to note was because there's such a large imbalance between the number of non-vote and vote examples that we have, and because we can generate as many swatches as we wanted, we made sure to use an equal number of votes and non-votes, and this also prevented overfitting. So we had very high model confidence as a result. But for running all the adversarial tasks that we presented beforehand, the drop model that we're working under is that we have model weights. We can run white box attacks. We can run FGSM, PGD, APGD. This is colloquially known as the white box setting in adversarial machine learning. And something we also like to do is,
For clarity, the sentence says combine model train on structures as both. You consider it structures are both. That's what this seems to be.
I believe that's a mistake. I believe that's a mistake. 90% of them are votes. Is what I distinctly remember. But I was going through.
Engineering structures that are very light.
Right.
That will come out of this trend.
Right.
So the whole point is that boundary should be cutting across the space of structures. They can't all be on the same side with the separate.
I was running experiments last night, specifically to, to explain the problem that I'm going to motivate in a second. I think you know what it is. I think Professor Fuller also knows that's what it is. That is wrong. So, thank you. I'll be correcting that. But to go back, the data set to the examples that we're going to be using, that we're hoping, will become adversarial examples. We're going to consider 500 marks and non-marks examples that are correctly classified by every model. So class-wise balanced, 1,000 bubbles, no swatches here. And we're hoping to investigate if our combined data set is going to be more susceptible to our adversarial attacks. Yes.
So this one is, are you considering the dots and the scribble from slides photos?
So that's something that we're looking to investigate. So that's actually current work right now, is to create marginal marks that more so resemble things like these, right? Because right now we're only considering our swatch examples over here.
We have a second data set where we're running the experiment. X's checks, partially filled bubbles, spiral bubbles. So we're redoing all of the experiments.
Yep.
And then once I look there, right answers.
It's
Then we'll not go to object first.
Yeah.
Right. Fundamental.
so we're handling it.
No, but this is a problem that, the reviewers have mentioned as well. So,
Is there ever just an invalid ballot answer, or is it always a yes or no?
invalid?
Like,
How do you mean?
like if I filled in 2 bubbles.
So we're
Oh,
Oh, would you just print it as telling fill in or not fill in on that?
yep. We're literally just,
What would this be?
Yep.
You don't need to be try.
so something really, really weird pops up is that when we run adversarial attacks on our models, we don't get anywhere. We don't get anywhere on both our trained combined and our trained balanced classifiers. Specifically, when we, I tried to go through and calculate the average gradient for all validation examples. And you'll see that the only setting, the only setting where we have any gradient information that's not exactly 0 is when we're taking the gradient on a non-vote 4 models trained on our grayscale combined data set. That's really, really bad for adversarial examples because we don't have a direction to add perturbations in. In fact, if we just run an adversarial attack, we're not adding anything, right? How do we visualize this? Let's go back to plotting all of our examples in an arbitrary latent space, right? But now we're going to add another dimension. We're going to add the gradient of loss. And we'll see for almost all of our food examples, they rest at this local minimum. Why is this? Our interpretation is that when you're, what a linear model learns, especially on this combined data set, is it's only learning if you're adding darkened noise to specific areas of these bubbles, right? So this is a weighted average instead of just, is this passing threshold, is it not? But that also means that if we're perturbing any other areas, as you can imagine, yeah. If we're adding any other noise over here, right, that's negligible because we've already filled in all these areas and made it classify as a vote. So any difference in our marks doesn't really affect our confidence. In the linear model for a support vector machine, our confidence is already classified. Our support vectors, their distance is as far away as possible. So even with very large epsilons, you're really not going to flip that vote. You're not going to pass that decision boundary. So we're going to introduce a heuristic to all of our white box attacks that will allow us to escape this local minimum and kind of do a bit of hill climbing, right? Because as soon as we're not at the bottom, we have a direction to the top. Oh, sorry. So here's how the heuristic goes, and we call it gradient look ahead. Imagine you're trying to flip a vote into a non-vote. And this is a bit weird to say, but you can imagine that the most perturbed example of a vote would be an all-white image. We have completely destroyed any trace of there being any mark whatsoever because there's nothing here. And likewise, if we're trying to flip a non-vote into a vote, then we want to destroy any trace of there ever being no vote. So it's going to be an all-black image. So this gives us kind of like a most perturbed example that we can kind of descend towards, right? So what we're going to do is we're going to take the gradient of our all black or white example. This is literally just a, all zero, all one example. We're going to add the perturbation in this direction, and we're just going to repeat this process until we reach a local minimum. Professor Hertzberg, did you have a question?
His hand's been up.
Oh, okay.
Doesn't mean he doesn't have a question. Just means his hand's been up the whole time.
Okay. So let's get into our results. Over here, we're really only considering our most successful attack, APGD attack. Did I even explain APGD? I think you guys were hammering down on me, during those few adversarial attack slides. Essentially, here, I'm going to go back. Let's correct this historical wrong. I discussed PGD. APGD is essentially PGD, but we're going to add a momentum term.
What's momentum?
Momentum is, that's a bit of a weird question. It's a weighted average between our previous update term and any new update term that we're adding. So whereas in PGD, epsilon step is the same for every iteration, because in APGD, we're considering the difference between our example in our previous term as well as any future update. We're going to try to slow this down. So you can see that those perturbations that we're adding at the very end, much smaller than they were initially. And what we found, this was our most successful attack. So across both data sets, across all models, and when we vary our perturbation factor, our epsilon, the magnitude in which we're allowed, the total amount of perturbation that we're allowed to add to our image, we find a nice monotonic behavior, right? As epsilon increases, we're more likely to flip more. Yes.
What are those numbers?
What are these numbers? This is our attack success rate. This is the number of misclassified, number of mis.
Well, no, it's not.
Oh wait, Jesus Christ.
That is how accurate the
Yeah, no,
classifier.
this is robustness. This,
What's robustness?
good question. Robustness is the number of correctly classified adversarial examples. So please ignore what I have on the slides. You can imagine that this is the attack success rate, 1 minus the attack success rate, right? So,
This is the accuracy of the classifier on attack.
Yep.
Period.
Yep.
So what do you want?
what do you want?
It's a number.
If you're,
If the classifier is resilient to the attacker, we should see what.
so if
What
you're,
is good? Is it one or is it zero?
well, if you're the voting tabulator, you'd love to see a 1. If you're an attacker, you'd like to see as close to a 0 as possible. Right? So if you're an attacker, your dreams are more likely to come true when your epsilon is larger, because at that point, you're kind of saying, I don't really care so much about visual imperceptibility. I care more about just flipping the vote. Right?
Sorry. Why would the adversary not care about his attack being visible?
Because when you're working under such a,
His attack is visible, he's going to be called.
Sure. I'm saying after a certain threshold with epsilon, right? The total amount of, right, you want to keep the amount of the total amount of perturbation that you can add to any image as low as possible while achieving a high attack success rate.
So we
In this
care
case, a
which
low.
column.
Hmm?
Tell me which columns are more important.
So,
0 out of 255 or the 255 out of 6?
so we decided that up to 4 over 255 to 16 over 255, that's when you're going to produce perturbations that aren't as visually perceptible past this point.
These are the 3 interesting columns because you cannot notice that an adversarial signal was injected.
Yes.
To say that.
Okay.
Then, okay, so now I'm looking at this, and if I see a 1, it means the attack does not work.
Yep.
So SVM is the perfect classifier. The attack never works on grade B.
Yes. Right. So this is the setting where we're not training on swatches. You'll see that no matter
It's a
how.
terrible idea to use machine learning. Twins is giving me a 0.5, 16 out of 255.
Exactly.
Concluding from just this 3 column and the twins row, don't use machine learning. Use SVM.
Let's not look at that. Let's just look at the SVM because that's our most simple linear model, right? What you're seeing here is that when you train exclusively on bubbles, until you add an irrational amount of perturbation at each step, right? You're not going to flip anything.
You're not going to flip anything.
But there's no reason in training exclusively on bubbles because that's already what a light sensor can do. The only motivator for using deep learning and classifying votes is training on the combined data set.
Hey,
Right.
So bottom of the table is the interesting part. I'm
Exactly.
down a little rectangle. There should be a color highlight that shows that these are the numbers you need to look at. The rest is noise.
Oh, I did that. I boxed it.
No. You're just looking like the 3 columns and all the methods. And over there, yes, accuracy dropped to 0.5.
Yes. Yeah. And that's really bad. Even in our lowest allowed amount of maximal perturbation, you're flipping all of the non-votes into votes.
But the sophisticated machine learning drops even further.
Exactly. You'll see that in twins as well. Once you reach an epsilon of 8 over 255, you can turn every single validation example into an adversarial example that'll be misclassified.
So don't use deep learning.
Don't use the combine. Well,
Use twins.
don't use twins. What do you?
This is so painful because it's such a.
I'm saying it's like these numbers are telling a very clear story. It says, don't use twins. SVM is okay if you have only bubbles, but the moment that you have marginal marks, right, those stashes, then it seems like your best bet is a plain old vanilla convolutional neural network.
Right.
That's your best bet. That's the best line on that table.
Yeah.
So you need to get that out, right? You're like circling the drain and not telling us.
And you also need to say, 95% clean accuracy is terrible. It's not good enough.
Yeah.
So having an SVM with clean accuracy in 95, it doesn't matter what its robust accuracy is, you can't get 5% of those.
The only reason why you would use deep learning is to train on marginal marks, on classifying something as their swatches. But what we've shown here is that it immediately makes you extremely vulnerable to flipping clean bubbled examples with the slightest amount of noise. So there's so much of a trade-off between, there's so much of a trade-off, there's so much of a security trade-off that it kind of negates the reason for using deep learning. Is that the conclusion you'd like?
Do you have bubbles?
The bubbles? You want to see the bubbles?
Is the next slide not bubbles?
No, it's physical.
I want to see bubbles. Okay, so you need to make it, so there's, a slide's always too complicated if you have to make multiple points on it. There's at least 3 points you have to make here, right? One is you need to say this thing you said about the combined data set. 2 is you need to say what's realistic. And 3, you need to make the point that you need to use a convolutional model to get good enough clean accuracy on it.
Okay.
You can't say all of those things in one slide, but like you need to say all those things.
Okay.
Right? We need convolutional models to get marginal things right. They are, the combined models make everything more susceptible. And combined models, you can add a small amount of noise and flip a large number of things.
Okay. What I'm really trying to show here is just with a linear model. But yeah, that's a fair point. Yeah. Pictures always go a long way. Yes.
So the degree B is the bubbles only, and the degree C is the combined.
Yes, that's the training set.
So my question, how is it possible that the single CNN is worse on the just bubbles than when it's combined?
Worse on just bubbles.
There's 0.99, 0 to 5, 3 E side, that was a 1 combined.
Oh, that's literally like one example. The 0 to 255 column is just the clean validation accuracy over all examples. That's
No,
that's
accuracy get better when you're training on a more complicated data set. Fair question.
Yep. There's also a bit of overfitting in the fact that you're only considering, there may be overfitting, since that you're only considering bubbles. So actually, if I could go up a bit, and I know what.
The hope is that you overfit less when you have actually draws a more realistic boundary to the table generalized.
And I know specifically what it is. It's that example. It's this example over here. It's like 1 or 2 of these examples that is fooling specifically the simple CNN.
Where they have like a very thick and dark boundary that like we consider both.
Yep. Good. See you, Tim. So let's get into our physical world, right? We haven't really explored our full threat model until we're printing, scanning, and registering ballots. And so we have to consider the scenario where any amount of perturbation that our adversary is going to be adding under some epsilon term is going to be printed, scanned, registered, and then fed into our machine learning classifier, right? So we really want to investigate when our adversarial examples are going to be translated into the physical world, when they're going to be on a physical ballot. So what are the scenarios where, an adversary could print this type of noise onto a physical ballot? There are 2 that we're going to consider. 5 minutes? We'll get through this. So imagine that we have a printer, a compromised printer. So in many elections, they allow for commercial inkjet printers to print ballots when they've already run out of ballots. We compromise this inkjet printer to add adversarial noise to a blank ballot. Then any bubble that's not filled in will already be counted as a vote, and each column will count as an overvote, right? So no matter where you place your vote, your entire ballot is going to be spoiled. Second scenario is our under. If we have this is the more severe threat model, and likewise a bit less unrealistic. If we have a compromised ballot marking device that will be printing your ballot after we fill in everything digitally, then we can, then we can print any example, any type of adversarial example. So this is the only scenario where we'll see a cleared in vote being potentially misclassified as a non-vote. And you could also imagine that the previous setting would apply here. Ayushi?
Sorry, so why is this worse than over? Why is under worse than over?
Well, no, I said this, my apologies. I said this scenario is a bit more unrealistic in that, the BMD does everything. Whereas this is a bit more of a fringe scenario where you're running out of ballots, so you have to resort to a commercial inkjet printer.
So let me do two corrections. One, if you could do this attack with a commercial inkjet printer, you can almost certainly do it with high quality, $100,000 printer.
Yep.
Two, this is more severe because if I can make filled in things appear as empty and empty things appear as filled in, I can completely change your vote.
I see.
If I can only make empty things appear filled in, I can add a vote to something you don't vote on or make you overvote. I can't change your preference. Here I can change your preference. Okay? So I can completely change what the ballot is.
You can change everything. So the way that we're going to be registering these ballots is any adversary, you have to perform these adversarial attacks in the digital domain, right? So to see if these adversarial examples will be successful once we, print, scan, and register them is we're going to take all these adversarial examples. And what we did for the sake of our experiment was print them out, is them all onto just some blank page. We printed this out using a commercial inkjet printer, scanned them, registered them using various sorts of libraries. But something that we found was the way that inkjet printers work is in order to simulate grayscale, they use this dithering effect. So say one pixel will be very black, one pixel will be, it works in binary, right? So one pixel is going to be all black, the other is going to be all white. So to a human eye, you're going to interpret that as grayscale. But because we're working with 40 by 50 pixel bubbles, there is a catastrophic difference between before and after printing. So what we did was we trained a denoising autoencoder that is going to take these printed bubbles and try to send them back to the space where they existed before they were printed and processed. And you'll see over here that kind of operates by adding a blur to everything. But these are much better classified by our machine learning classifiers, which were trained on non-printed bubbles. So let's see how our attacks fare in this scenario with a bit of motivation. In this scenario, we're only really going to be considering our combined models. Again, they're more realistic. They fit our incentive more of using deep learning here. We're going to be running just our most successful APGT attack on 500 marked and non-marked bubbles. And kind of what we want to see here is if any adversarial examples translate at all. Because there's a huge process in the pipeline between, is our adversarial signal going to be removed when we print them or removed when we denoise them? Is this going to fool anything? Is it going to fool anybody? So considering both attack settings, only attack setting that we found that worked was the over setting, where we're trying to flip a non-vote into a vote. Specifically, if we just zoom in onto our SVM, we'll see that even in our lowest perturbation magnitude setting, we're able to flip 2.2% of our non-votes into votes. Of course, this is a far cry to the virtual domain, but when we consider that we can overlay the same non-votes onto as many ballots as we want, there are a lot of consequences. The other thing that we found over here was that our undersetting, when we're trying to flip a vote into a non-vote, didn't produce any successful adversarial examples at all for any model. So the takeaway here is that over is our only viable attack setting. So to conclude, we have two real world scenarios that could potentially print ballots that then will become misclassified by a tabulator that uses deep learning architecture. But the only attack setting that works are over attacks. We found that they're the most efficient in both the digital and the physical world. And there's a lot of future work here in one, mitigation techniques against, to try to combat the susceptibility to adversarial attacks. Why not include adversarial examples in our training set, right? Two, there are a lot of different attack norms. So we've been adding perturbation in what's called the L infinity norm, where the difference for each pixel between our ground truth just has to be less than epsilon. But we can also add noise in, say, the L2 domain in Euclidean, by Euclidean distance, and see where that takes us. And three is to use black box attacks that don't even use any gradient information to try to print adversarial examples.
And Amir, just to answer your question from earlier, the way we found out that the gradients were vanishing is we ran black box attacks and they worked better than white box attacks. So we have run black box attacks and they work, and so we do have some success in the setting where you don't know model weights. And that's how we actually figured out that, we didn't have gradients for most of our examples for our white box attacks.
So that's everything. Are there any questions on? Sure.
Yep. What is specifically the receptacle?
Yes. Yep. So, oh, sorry. That's in. So you can imagine over here, right? Whatever ballot you're adding, these are all going to be adversarial examples. They look like non-votes. They are non-votes, but to a machine learning classifier, they register as a vote.
And just what these actually look like, if you really look closely, they're like 40 by 50 pixels, but if you look closely, it looks like some Gaussian functions.
By the way, these are adversarial examples. Yep, but that's as much as you need to really fool a machine learning classifier. You can't even see that because that's our lowest epsilon setting.
But if you go to really high epsilon, if you go to epsilon 255, it literally just blacks the whole thing. But these are misclassified with if you really look, it's a little bit less.
So then, it's coming down to just use two different scanning techniques to take together. Like you scan it with like IR or UV, and that'll again grab that and off of that.
So that's possible, but then the other thing becomes the printing process itself adds so much noise, right? As in, maybe a stray pixel is just going to turn up as black, that it becomes very hard to detect what's maliciously added noise and what's just noise because we're using a inkjet printer. So.
Right, but like, so this is a very common defensive technique, is I'm gonna train multiple models. Right, like, same thing you're saying, multiple models and make sure they all agree. Right, like if models are disagreeing, well, maybe I think something's going on, or it is specific. So absolutely.
Professor Hertzberg, you had a question?
Yeah. So again, I want to just understand. So the attack would require still to be run at the learning phase. So it's before the elections, right? You're not at a local voting place and there is a printer there, sure, but the learning should have been done in advance, right? That's at least my understanding. So I'm not completely sure the inkjet printer scenario, how it would actually be relevant. So you assume that in the learning, to prepare for the possibilities that you will have an inkjet printer, then you will also include input from an inkjet printer, and at that point, the attacker will do the attack. Is this what basically the scenario we're talking about? I'm trying to understand the attack scenario. So obviously, and the inkjet printer was, of course, made a lot of sense. You said there could be a situation where there is no, you don't have enough forms, you print in a form, sure. But,
right, so yes, Amir, it's what you said, is that voting machines, a lot of them in their actual specification say we'll take commercially printed ballots of this weight, as well as like residentially printed ballots. We just care about the paperweight. So
yeah, I understand. So, but again, the learning was done in advance. So, are you talking? Unless I'm completely misunderstanding how the process works, but I would be quite sure the learning has been done in advance, right? And your attack has to be in the learning phase, correct or not?
No. Our attack's in the evaluation.
It's when you classify an actual image on election day. Take a ballot. The ballot was modified by the attacker at 4 in the morning because he came with a printer. He put this Gaussian noise, this very light pixels that darkened the bubbles a little bit. Then when a voter came, he picked up a ballot that he doctored in the morning of. He puts his mark where he wants. Then that is fed to the scanner. And the scanner classifies these adversarial marks. So the classification comes out wrong. It's not attacking the learning, it's attacking the normal classification. The defense would have to actually say.
But the gradient is already defined at this point. I can't understand exactly how it works. The learning, all of the learning parameters are already fixed. So how does it work?
So you're using the learning parameters to create an image that changes the classifier output without being very different.
We assume that the weight of the classifiers of the neural network or the deep learners, these are public. Imagine that the weights are public.
Yeah, that is, I already understood that I need to accept this, although I'm not happy with this assumption, but I understood that I need to accept that you assume that the parameters are all public, right? And then you're saying you use these public parameters to identify examples which are borderline but will not be viewed by persons. I mean, you didn't check that they are not viewed by persons, did you?
Well, normally that's the amount epsilon of noise being added to the image. When Caleb was showing that you're doing xi plus epsilon times the sign of the that was adding that imperceptible amount of noise. So the requirement is that this epsilon that you're adding is small enough. If it's too big, you're adding something that will be visible and the attack doesn't work. So the epsilon needs to be small enough, the smallest you can.
And these epsilons that we're using, well, we're taking them from prior work on what's considered visually imperceptible.
Mhm.
And like the examples do look clean. Like these are actual examples here, right?
Right. So
Yeah.
that's
What
very
you mean by that
impressive.
is-
So you're saying that these examples, when you give them to a learning algorithm that was not modified, right? You just learned
Right.
these parameters, and yet you were able to show that these learning algorithms, when they get such examples, they are still. I mean, you take as an example, you just do a very simple algorithm, it would give you the correct result. You don't need a very clever algorithm for that. But you're saying,
Right.
because you've been trying to have an algorithm which should be much stronger, it actually does have these special cases where it fails. Is this a correct interpretation?
Yes, Amir.
Yep.
Okay, that's really cool. Okay, thank you.
And all you need is one really, really, really good example that you can print over and over and over again.
Yeah,
As
sure.
we've shown on this slide.
Hmm. Yeah.
Right, like
Okay.
I don't have to misclassify all votes. I just need a thing I can print on 1,000,000 ballots.
That's what makes this stuff so dangerous.
Yes, right. But then there's also the issues that you're learning. I mean, if you want to do anything here, you will need to modify. I mean, there are different candidates, right? Your goal as an attacker of the system is surely not just to have everything just misclassified as no vote or something like that. It will not be useful for an attacker. The attackers need somehow to modify a particular ballot to either a different one or to right, but it has to be for a particular, right? You agree? Or no?
Yeah,
The attacker has to decide when he sees a ballot, should I actually, or, I mean, here the idea is that the attacker is putting this noise on blank ballots up front. What's going to happen in practice is that when the voter puts 3 marks on it, he may end up having something that where the machine rejects his ballot, denial of service, because the ballot looks like it's overvoted.
Yep.
Because the voter puts something in one place, and then the adversarial signal in another ballot, now the blank appears a vote, resulting in overvote. So that's what could happen. But imagine that the voter did not fill in one of the bubbles and left the race empty. Then that race that was empty, the adversarial signal, if it's placed always on the candidate Joe Sixpack will pick up votes that were never made. And you can win the race as a result.
so
Okay, so
on,
you know that a particular bubble will be for a particular candidate that you don't want, for example, or a bubble will be for the candidate you want. So you will pre-fill in an invisible way that bubble. And if I fill a different bubble, then there will be a conflict and my vote will be rejected. That's the idea.
Yep.
So you end up having either an overvote and the ballot is rejected, it's denial of service, or the thing silently puts a vote for Joe Sixpack, your hidden winner, and you actually change the outcome of the election.
Yep.
So both scenarios are problematic, and you don't want them to happen.
And what we're aiming for here is, because it's already a bit of a fringe scenario to be using an inkjet printer, you just have to flip enough votes to, say, flip a local election, and then flip a county, and then maybe even flip a state. And as you can imagine, there are many such examples in voting.
I mean, it's not difficult to understand. Take the margin of victory of a typical race. If it's something like 1%, you have to actually manage to pick up 1% of the ballots that had left the race empty, have the adversarial signal on your desired winner, and then for these ballots, they will get picked up. If you have at least 1% of them that left the race empty, all these guys will now all of a sudden go to a specific winner and you change the outcome.
but it's by far, the attack is much more effective on races where people often don't vote.
Yes.
So, so in the 2020 presidential, I looked at the 7 battlegrounds for 2020. state congressional races for 2020, only about 80% of people fill them in. So you can have a pretty significant, right, you have about 20% of ballots that you can play with there to like impact their vote, because a lot of people just vote for president and that's it.
So
Imagine that the president's race, you can't do anything about this one because everybody votes it. So it's going to cause either it will go through because the person picks the same candidate as your adversarial signal, or it creates a conflict and you have an overvote and the ballot gets rejected. Then people will say, "What? There is nothing on my ballot. My ballot rejected."
So in that sense, there are just two things that can happen here. One, either you cause an overvote because somebody either lays down, their mark over there, but there are multiple other, empty bubbles that will register as a vote to a machine learning classifier. Or two, you just place one vote on one of these bubbles, and when somebody does not fill out, say, the last position in a local election, that person becomes elected, or that person gets that vote.
So we're way over time. So I wanna stop, mostly because I wanna talk to Caleb too. But let's stop there and thank Caleb again for that. We can change. Okay, yeah, let's stop, and we don't have a talk next week, right? I assume.
Yeah, but I need to cancel the lunch.
Okay, good. Yeah, please do that. All right, thanks very much, everybody. Have a good
Thank
break.
you.
We'll
Thank
see
you.
you next semester.
Marion, would you like to take your log off? Could you just log off of my
Stop
account?
recording, yeah.
I'll make it fine.